Hey everybody, in this video I'm going to be covering system design and general web architecture. You want to know this stuff because it's important for advancing your career. If you want to go from a junior developer to a senior developer, you're going to need to know this stuff. As you get promoted, you'll do less direct coding and focus more on design and architecture of the applications you're working on, which is what this video is all about. I'll be starting off with an overview of what distributed systems are and why people and companies use them. Then I'll go into some ways to measure performance of these systems and how to do quick math to estimate the requirements in terms of traffic and resources for a project. After that, I'll go through the main parts that make up these applications and then some of the concepts related to scaling them. Those will include load balancers and content distribution networks, database design, caching, and then horizontal versus vertical scaling. Finally, I'll end the video by designing a YouTube-like video streaming application from scratch in the style you'd see during a job interview. So what is a distributed system? Why would you want to build one? And what are the pros and cons? A big issue with learning this stuff is that there's a lot of jargon and buzzwords which can be really confusing. So one of my main goals here is to simplify this stuff and clean up some of that confusion. Another big thing before we even go into the nuts and bolts of distributed systems is that really it's important to emphasize that you should always keep things as simple as possible. MIT's own professor who teaches their course on distributed systems says that whenever possible, you should avoid using them and just avoid the pain involved with managing them. Google and Facebook and Amazon, all these big tech companies you've heard about, they didn't make their distributed systems for fun. They did it because they had no other choice available to reach the scale they needed to. If they had their choice, they'd have some sort of magical computer. Their applications could run on a single computer that magically handles all that traffic. But in the real world, we don't have that option, and that's when you turn to these more complicated distributed systems. A lot of engineers lose sight of that, and they either just want to improve their resume or make something cool, and they end up making something that's very complicated and doesn't work properly. So if you learn nothing else from this, I'd say that it's to always keep your design for your applications as simple as possible, and then only change things once that's required. So with all that out of the way, what exactly is a distributed system? Basically, it's a group of computers working together, and the goal is that all that complexity should be hidden completely from the user. So to the user, it's like they're just interacting with a single computer. Behind the scenes, when you think about something like Google, Amazon, Facebook, they have multiple data centers with hundreds of thousands of different servers, but to the user, all that complexity is abstracted away. They have no clue that all that is happening behind the scenes, and that's what this diagram shows. To the user, they just have this magical distributed system. It could be Facebook, whatever. They make a request from their cell phone or their laptop. Behind the scenes, all these different services are working together, and they return a response. So all that stuff is hidden away. It's like a magical little box, basically. Obviously, this isn't an easy task, and that's why software engineers make so much money at these big companies. Billions of dollars have been invested in research and development to figure this stuff out, and that's some of the issues that arise with these systems are what we're going to cover coming up next. So that brings us into the so-called fallacies of distributed systems. So operating at a huge scale requires an entirely new way of thinking, and most programmers, when they come into these big companies, they haven't been exposed to this type of stuff, so the fallacies are these kind of wrong assumptions that most programmers have the first time they're exposed to these systems. They're real issues, but they're also kind of an inside joke. So the first one would be that the network is reliable. When you're running your small application on a single machine, you don't have to worry about network issues that much. When you're doing a distributed system, you have thousands of machines talking to each other, and the network will often break at some point. Latency, you're going to have latency between those machines as they're talking. Bandwidth, when you're moving data around all those different servers, that becomes an issue. The topology of your network, that's going to change as servers go down and other ones get brought up. That's going to be something you have to compensate for. security within your network, the fact that only one administrator, so there's going to be multiple people working on the system and potentially changing it, and that the cost of moving data around is zero. So these are some of the main things that as a programmer you're not really thinking about when you're building small scale stuff, but that it becomes a big issue when you're working with distributed systems. Some common characteristics of distributed system are, first off, that they don't have a shared clock. So all those individual servers are running on their own time, and this leads to an issue called clock drift, which is where the timers on each computer get out of sync, which can lead to big issues with ordering of events and stuff like that. You could theoretically, if you don't handle this problem, get an error where it seems like there's negative latency. It's like time travel, where because one clock is off on a computer and it sends a request to another, it results in basically big issues related to the timestamp on those requests. So Google did a study on it and said that if you only synchronize your servers once a day, you can get a 17-second drift in either direction, which could obviously cause a huge issue. If you have something like a stock exchange or some sort of auction site like eBay, and somebody on either side is off 17 seconds and they can basically game the system, that's going to be a big problem. So Google, to handle this problem, they actually use a combination of GPS receivers and an atomic clock, and they call it TrueTime. So they have a pretty complicated system to take care of that issue. No shared memory is pretty obvious. Each node or server in your system is going to have its own RAM, its own storage. So if it needs data from somewhere else, it's going to have to request that from the part of the system that does have it. Resource sharing goes in line with that, which is that anything in your distributed system should be able to be shared between nodes on the system. So that could be hardware, software, or data. And then finally, you have concurrency and consistency. So the different parts of the system are going to be working together and working at the same time, and you want to make sure that there's consistency between how that all works. Since information needs to be passed around our distributed system, they obviously need some way to communicate. So there's a lot of different strategies to do this, but at the most basic level, it requires some sort of uniform format or protocol so that the different parts can understand what the others are saying when they pass messages back and forth. You can kind of think about it like a just general human language. Like if somebody's speaking Spanish and somebody else is speaking English, you're not going to be able to talk to each other. And that's similar to how it is with computers. These communications, when you're doing them at scale, there's a lot of things that can go wrong that you might not think about, and you need to be able to handle those. So in one case, you have a client can't find the server. It sends a request, but the server is not responding. So you have to have some way so that the client can find another server that can serve it. Another one is that you do find that server, you get the request across, but midway through while it's processing, that server breaks down, and now you have to figure out a way to resend that request. The alternative is that the server has a response, but the network fails, so it tries to send it back to the client, but the network fails halfway through, and now technically your server thinks it's done its job, but the client still doesn't have the response. And finally, another way that the communication can break down is that the client itself breaks halfway through the response. The server has nothing to send it back to. So you have to have some way to, maybe in that case, the server stores that response until it detects the client again, and then it can send it out. But a lot of stuff that with smaller scale stuff you don't have to worry about, but when you're dealing with distributed systems, it becomes a big issue. So all this stuff sounds pretty awful. The benefits are why people deal with all these issues. So first off, it's more reliable. If you're running on a single machine, if that thing goes down, your whole system goes down. Next, you have scalability, which is kind of an aspect of that as well, which is that because your whole system is designed to work on multiple machines, it's very easy to just add a few more machines or nodes, whatever terminology you want to use. So if you are gradually getting more traffic, it's really easy to just add some more nodes and scale up. You also get the benefit of lower latency, which means that because, once again, you're distributed, you can have your application running out of multiple data centers all around the world, and that means you're closer to the user, so it's reduced latency, increased performance, and finally, it's more cost effective. At some point, you just can't buy a larger single machine, and with a distributed system, you can buy a bunch of commodity servers that are very cheap. You can buy them in bulk, and then you can just run your software off those. So now let's look at some performance metrics related to system design and see some common ways to measure the performance of a distributed system. First off is scalability, which is the way our system grows and manages increased demand or traffic. It could be the volume of data per request or just the total number of requests over time increasing. Our goal is we want to achieve this growth without a loss in performance. Bad system design could result in a bottleneck on the number of users or traffic our application can handle, or it could result in exponentially increasing cost to serve a small increase in traffic. Next we have reliability, which is a probability that a system will fail during a set period of time or perform as required without failure during a certain time period. It's kind of harder to define with software compared to hardware. With hardware, you know, like if a CPU or a hard drive has failed, it's pretty obvious. Software, there's almost degrees of reliability where responses could slow down. They're still accurate, but they're just slower than normal. Do you count that as a failure? It's just kind of a harder to define. An overall system is reliable if it keeps working even when software or hardware components fail. So that means we need systems in place like automated testing to prevent bugs from being deployed to production. You also need tools that can predict and compensate for hardware failure so that before a server even fails, you can be notified and you can preemptively take that server offline and repair it before it starts serving bad requests. A common way to measure reliability is mean time between failure. So you take the total elapsed time for a time period minus the total downtime, and then you divide that by the number of failures. So in this case, we have 24 hours total. Let's say you have 4 hours of downtime, and that 4 hours of downtime was caused by 4 different failures. What that means is that you have 5 hours on average before your system will have a failure. Availability is the time a system remains operational for a given time period. This is probably the most important metric when it comes to your users, is whether your site actually works and what % of the time it works. So poorly designed software, it's not as common now, but back in the day you might remember times when you went to a site and it says, sorry, the site is down for maintenance. That was before a lot of these best practices and new tools came about. For stuff like updating a database, you might need to take the entire website or application down, and that would usually involve some poor software engineer staying up till 3 a.m. or whatever time is slowest for that website, and then they'd take the website down, do whatever upgrades or changes they needed to do, and then they'd deploy it. Nowadays, that's not as common, but that's an example of something that poor design will hurt your availability. The way to calculate that's pretty simple. You just say available time divided by total time, and then you multiply that by 100 to get your percentage. So if your website's available for 23 hours out of the 24-hour day, it's 95.8% available. This kind of shows just your general availability percentages and what that equals for annual downtime. It's kind of a different way to think about things, because 99%, like if you're taking a test at school or something, that's a great score, but for software, 99% availability is terrible. That's 3 days, almost 4 days out of the year you're down. And for a big company like Amazon, you're talking billions of dollars if your website is down for 3 days out of the year. A common metric that you might have heard of is 5 nines, which is this bottom right here, and that equals 5 minutes out of the year that you're down. That's a pretty common service level agreement for many companies. I'll also say it's kind of hard to measure overall software system availability, because certain parts might have, if you're running like microservices, some might be less available than others, but you can cover that up by having redundancy. So even if one replica breaks, you can have a redundant copy that can take over for it, which covers up for the overall availability. So if one application technically has 99% like reliability or success rate, you can still have a much higher overall availability because you have redundant servers and replicated servers that can take over. So if a request fails, you can have like a load balancer that detects that, and then it can resend that request so the user doesn't realize that failure actually occurred on the back end. So it can be kind of hard to calculate that, because as long as it doesn't affect the user and it doesn't affect that you're making money, does it really count? There's different ways to kind of measure that. So reliability versus availability, they sound pretty similar, and it's kind of confusing for me initially when I was learning it, but there is a subtle difference. So if a system is 100% reliable, it will always be available, because that means that essentially you're never going to have any errors, nothing's ever going to break. That's not going to happen ever in the real world, but you should always aim for more reliability because it's always going to give you more availability. Like I said earlier, you can compensate for a non-reliable system by having replication and redundancy in place, but there's always a risk that if those software systems that compensate for the lack of reliability break, all those flaws in your software will be exposed and you'll see a lot of downtime as a result. The benefit of writing reliable software is that you need less resources dedicated to those replicas and those redundant servers, which means that you're going to be more profitable just because you need less hardware to serve the same amount of traffic, because you don't have to have a bunch of extra resources on hand to handle your failures. One thing also is that you should, the requirements like the service level agreements, the availability, that's going to depend on what exactly the purpose of your software is. In some cases, like social media, it's not exactly the end of the world. If you try to create a post and it fails, it's not a terrible disaster. So it might not be worth for a website like that to invest tons of money into high reliability and availability. On the other hand, if you're like SpaceX and you're shooting rockets into space, you're going to want to make sure that your software is reliable, because there's $1 billion worth of hardware on the line. If it explodes, there's potentially people that could die. So you always have to keep in mind what you're shooting for, what your goal is, and how necessary is it worth the investment for all that extra, to invest all that for the availability. Example would be a plane. So a plane, you could cover up the reliability by having a fleet. So if you have a plane that needs routine maintenance, you can have a backup plane that rolls out and takes over that flight. But for a plane, the number one thing you want to do is make sure it's reliable, because once that plane's in the air, you do not want a failure. So this is just a real world example of what I was talking about earlier, where depending on what you're doing, the trade-off of availability and reliability is going to be very important. Next up is efficiency, which is pretty simple to understand. It's just how well our system performs. Two common metrics are going to be latency, which is how long a request takes to get back to the user, the delay, and also the throughput, which is the total amount of requests and traffic that your system can handle. A poorly designed system, it's going to hit a limit somewhere, like maybe you have a bad algorithm somewhere that scales exponentially. The result could be that a slight increase in traffic dramatically increases the latency and your users are going to get frustrated. Finally, we have manageability, which is the speed and difficulty it actually takes to work with and maintain your system. So an example would be that you have the fastest car in the world, but it's impossible for anyone to drive without crashing it, so it's basically useless. It doesn't matter how high performance it is if nobody can work with it. Some factors that go into this are how easy it is to find bugs. So if you have a really complex system, you don't know where the origin of an actual bug is. It could be in multiple different services. So that's one thing. How hard is it? How observable is the system, and how is it? How do you find bugs when you're working with it? How easy is it to deploy updates and new features? If it's something that's really complicated and high risk, people are not going to want to take that risk, and your creation of new features is going to slow down, which is going to impact your success as a business. The goal really should be to abstract away that infrastructure so your product engineers don't even have to think about it or worry about it. They just write their code and deploy it, and that's all they really have to think about. Next, I'll be covering some important numbers and concepts all programmers should know. It'll help you in pretty much all areas as a developer. For example, if you want to estimate cost of your own side project before you take the time to implementing and writing a bunch of code, you can use this stuff to make those rough estimates and give you an idea whether it's even profitable. It'll also help you avoid a nightmare scenario where maybe you have a small side project and all of a sudden it goes viral and the person's left with thousands of dollars in cloud hosting bills. I've read about that all the time. So this can help you get a rough estimate of where you should set a billing alert or shut down the service automatically rather than risk losing a bunch of money. It's also useful for if you're working in a company and you're thinking about adding a new feature and you want to estimate how much it would cost per user to add that feature. You can do a rough estimate that way. It'll also help you with general system design so that you know what the trade-offs are, what are the areas that are going to hurt performance of your application, and in the simplest way, knowing this stuff, if you're doing an interview for a job, it'll really help you on those system design type interviews. First thing we're going to look at is latency, which has a big impact not only on user experience, but also on how you design your entire application to reduce latency. So over here we have the actual times, which are kind of hard to wrap your head around because it's nanoseconds, milliseconds. So I've converted this to actual, more understandable. I've scaled it up to 1 second for CPU cycle, and you can see how it gradually goes down. So this is like when you're running calculations, your CPU can cache data that it needs, and it can perform those calculations very fast. Once you have to start reaching out to other areas to get the data you need, things start getting a lot slower. So RAM, or main memory, this would be stuff like if you've heard about caching. This is still pretty fast. So you can see it's 6 minutes, so it's not bad, and it's much better than going out to disk. So if you've heard about how database calls are slow, this is why, and you can see the difference between grabbing something from a cache like Redis or going to the database. It goes from 6 minutes to 6 days, and that's with a more expensive and up-to-date solid-state drive. If you're using an old-school hard drive, it goes up from 6 days to 10 milliseconds, which converts to 12 months. So that's a massive difference. And even worse would be calls to other data centers. So here you're limited by the speed of light. So if you have to, if you don't have data locally in a certain data center and you have to go reach out to another one, you can see that your performance drops off horribly. So that's going to come into play when you're designing a system. You want to make sure whenever possible that you have your data locally so that you can run your app faster. Milliseconds might not seem like a huge deal, but if you've ever been playing an online video game and you've been lagging, you can tell how frustrating just a few extra milliseconds can be for your users. So that's something you always want to keep in mind. To help make more sense in your head, I've drawn kind of a diagram of how you can picture this, because just the numbers doesn't really help you much. So let's say in this case you're working on a problem like a application would be. The CPU would be kind of, to extend it to a desk or a real world with you as the computer, the CPU would be your brain. It's stuff that right off the top of your head, whatever data you can memorize, you don't have to really go and access it. So it's obviously much faster. Going to RAM would be like having a book or something on your desk that you can quickly flip through, grab the information you need, and then do whatever you need with it. Beyond that would be disks. So maybe you have like a library or a bookshelf in your own house. So you leave your office, you go to that bookshelf, you grab the book you need, get the information you need, then you go back to your desk. A network call outside the data center, which is obviously slow, would be like walking to the library, having to check out the book, get the information you need, then go back to your house and use that information for whatever you're working on. So the obvious takeaway, and to kind of make it more concrete, because numbers always don't work as well as a visualization, is you want to, whenever possible, keep the data you need close by to your application. The key takeaways then are you want to avoid network calls whenever possible. You also want to avoid hits to your database, so keep frequently accessed data in memory with a cache if possible, rather than continuously going to your database. A lot of distributed system stuff is related to latency and how to deal with that. So, for example, one reason to replicate data is obviously for disaster recovery. You want it so that if one data center goes down, you don't want to lose all your data, but it's also beneficial to have that replicated so that, if necessary, you can serve it as close to the user as possible. And that's the same concept behind CDNs, content distribution networks, is that you can take advantage of having a service that gives you and serves your data as close to a user as possible. Another example, this is MapReduce and kind of how it would work. So Google, early when they were scaling, they had big issues with networking inside their data center where they had too much data moving back and forth. And to help solve that issue, they created MapReduce to do bit calculations on big data. Instead of having one big server run those calculations where it would have to reach out to other servers that held the data, pull it back through network, and run the calculations on it, they created this system where they were able to have each server that already held the data, it would run the calculations locally, and then it would send the result to another server that basically puts together all those different calculations and gives you the end result. And that was all to reduce network latency and the amount of bandwidth going through their data centers. So the example here is like, the equivalent would be, let's say you got a bunch of different piles of rocks. These would represent servers with data on them. The obvious way to do it, which is what MapReduce does, is that you would go to each of these, you would count the rocks, and then you just add them together. The naive way, which is how a lot of applications actually work, if they haven't taken this into account, is that it would be like going to each of these piles, grabbing the rocks, moving them back to where you were, and then counting, going back, moving all back here to count from the spot you started at, and just continuously doing that. So you can see how inefficient that would be, carrying things back and forth rather than just walking to them, counting right here, and then going back and using those results. So that's kind of another real-world example where the stuff seems really complicated. Stuff like MapReduce, when you hear people talk about big data and all that, seems very complicated, but it's really not. The concepts behind it, if you use a real-world example, are pretty simple. Next up, we're going to go over some quick math for making capacity estimates so that you can kind of get a rough figure of the type of resources and server amounts and stuff like that you're going to need. First up are some basic data conversions. So 8 bits equals 1 byte, and 1024 bytes is actually 1 kilobyte. So that's a pretty frequent error, is that you assume it's like metric, so it'd be 1,000, but because computers work with binary, it's actually 1024. So it's not a huge deal when you're making rough estimates, but it's always good to know that. So you can see that same value for each megabyte, gigabyte. You've probably heard about those all before, but we're going to be using these conversions for when we're making estimates. Common data types, so a char is 1 byte. That is, so if you have like messages in your application, you're going to have every character in a string is 1 char. You're going to have integers, which are 4 bytes, and that, if you think about why that is, if you've heard about a 32-bit integer, obviously 32 bits, one byte is 8 bits, so you have 32-bit integers, 4 bytes. And then you have Unix timestamp, which is 4 bytes. So it's always good to know your time conversions and just kind of maintain these or memorize these so that you can make quick estimates for daily traffic. Really common is like requests per second, how many you need to handle, and stuff like that. So you can see, obviously 3,600 seconds per hour, multiply that by 24, you get 86,400 seconds per day. And roughly, if you want to estimate rough monthly traffic, you got about 2.5 million seconds per month. So once you know how many total requests you're getting, you can just divide it by each of those values to get requests per month, hour, day. So it's always good to have those conversions probably memorized, just because it makes things easier. So now let's put this into practice. We're going to do some example calculations for an Instagram type app. So first up, we'll do a traffic estimate, which the formula for this is going to be your average daily active users, and then you're going to multiply for average amount of reads per user and writes per user. So in this case, we're going to say we have 10 million average daily active users, and the average user, they view 30 photos. So that's like they refresh their timeline, maybe they scroll down a couple times and they see 30 posts or 30 photos. And simple math, that means you're getting 300 million photo requests per day. For writes, we have the same amount of daily average users, but some people will upload multiple times per day. Other people will upload maybe once a month. So that gives us an average of 1 per day per user, and that gives us our 10 million. So then we can use these times. So this is our daily numbers of seconds per day. So every day, taking this, we can see we got 3,400 requests per second and about 115 writes per second. And this is usually a pretty, in almost all cases, a web application is going to have much more read requests than writes. And getting this, knowing your average users, how much requests they're making, that's why people talk a lot about analytics and stuff like that. It's very valuable to have that information so that you can make these estimates. It's also worth noting that external requests don't always equal the same amount as internal. If you're using microservices, it's pretty common that one external request like this could cause dozens maybe of internal, because you have to make calls to the photo service, microservice. You might have a video service, analytics, logging, all that type of stuff. So one external request is going to mean probably you're going to have more internal requests, but for now that's really not a big issue. Next up we have our memory estimate. So for this we're going to use that value we got for our read requests per day times the average size of our request, and we're going to multiply that by 0.2. And the reason for that is our 80-20 rule, which is that generally speaking, for a rough estimate, you can assume that 20% of your data will be 80% of your overall requests or traffic. Not all, especially on a social media site, some posts are going to get much more views than others. So a popular account, their post is going to get viewed millions of times. Other people's posts might not get viewed at all. So to help save our database, what we're going to do is cache our most popular stuff, our most frequently accessed data, to, like we talked about earlier, reduce latency. Instead of serving our popular data from our database and disk, we want to store that in memory to really speed up how fast users get that information. So we're going to take our 30 million requests, and we're going to make an estimate that for like an Instagram post, you have the username, you have stuff like the description, the written text. We'll just do a rough estimate of 500 bytes per post, and that comes out to 150 gigabytes. We then multiply that by 20% or 0.2, which means of that total data we have 150 total. We only really need to store 30 gigabytes of the most popular or most frequently accessed. And then we also need to multiply that. We want replication on our cache. So for a rough case, we'll have 3 total cache servers, 2 as backups, and that gives us a total of 90 gigabytes, because we don't want a single cache server. Like technically we could save money by only having one with the 30 gigabytes, but if that goes down, then our entire application is going to be in trouble when we have a bunch of requests going to our database. So now bandwidth requirements. The formula for that is just requests per day again times request size, so 300 million requests again. For this one, we need to account for also the photo that we'll be serving. That would generally be served from like a CDN. So we're going to estimate the average photo size once we compress and stuff is 1 megabyte plus the 500 bytes from like the text and username and all that other data. So that comes out to 450,000 gigabytes per day. And if we divide that by the number of seconds in a day, our peak, or our average actually, bandwidth is going to be 5.2 gigabytes per second. It's worth noting again that rarely is an application going to have like a steady flow at the same rate. You're often going to have a lot of peaks where at your highest usage time you might have 3 times the bandwidth, and during dead times you might have a much lower amount. So Netflix, for example, Once people get off work in the US, they obviously have much higher peak traffic compared to during the working day, because at least most people aren't watching Netflix during the middle of the day. And finally, we have our storage estimates. So for this, we're going to take the number of writes we get per day times the size of those writes and times the amount of time we want to store the data. So we get 10 million writes per day. Average, like it was before, 1.5 megabytes for the photo and the other information, which comes out to 15 terabytes per day. We take that, there's 365 days in a year, and then we also, you're going to want to hold stuff for a long time, 10 years, maybe longer, if you're an established company. So you can estimate that long-term storage is going to be around 55 petabytes. So you'd use this to estimate all these things we've gone over. Once you have your analytics and you can say, okay, for our average user, we're making this much money. If it's an Instagram, you can calculate how much money you're making per user on ads, and then you can look at the storage cost, the bandwidth cost, all that other stuff, and you can then find out if your idea is profitable or not. So that's pretty important. Before you take the time to make an application and go through all that effort, you want to see if it's even viable. Even if you don't have the user analytics data because you haven't actually tested anything, it's a good idea to at least try to estimate this stuff so that you can, if you're pitching to a venture capitalist or whatever, you can at least give them some sort of estimates. So that's it for this video. I just want to go over some quick numbers and math, not go really in depth, but give you an idea of what type of stuff you should be paying attention to. I think it'd be a good idea to take some of these conversions, think of some different ideas for an app. So this, we did a photo app. You can come up with maybe a video streaming app or something else and run through some calculations, use these formulas, and just do some practice, and it'll become pretty natural after a while. It's not like it's real complicated math. It's mainly just converting between units and doing stuff like that. So I think that's a good practice that you could do. Now let's go over the two main ways to scale a web application, which are horizontally or vertically. We'll be going over the pros and cons of both, and then looking at the trade-offs between the two options. So let's say you have your own web app, it's running on a single server to start, and the number of users is rapidly growing, which is obviously a good thing, but those users are starting to complain that your application is running slow, and that's due to the volume of requests increasing so much. So there's a couple different ways or reasons this could be happening. First would be CPU. If you're doing a certain function that requires a lot of processing power, that's obviously going to eventually overwhelm the CPU and slow things down. Same thing with memory, where if your app is doing something where it needs to hold large chunks of data in memory, that will get full and it won't be able to process as many requests at the same time. I/O is how fast your application can read from storage. So if you're doing something where you need to access images or video files stored on the hard drive, you're going to have a limit to how much data you can access at once. And also, the last way would be bandwidth, which is if you're streaming or doing something like that, the amount of data you can push through the network is also limited through a single server. The simplest way to solve these problems initially is pretty kind of common sense, which is if your server's running slow, just get a bigger server. And that's what vertical scaling is, where you take your initial server, you upgrade whatever area your server is failing in. If it's CPU, memory, whatever, you upgrade that specific area on the server, and your web app scales just fine. The problem with this is that there's diminishing returns and limits to scalability. So something like Google, they have data centers all around the world and have hundreds of thousands of individual servers. There's no way you could scale and have a single server handle all that traffic. You'd have to have a server the size of a mountain, and it just wouldn't work, obviously. There's also diminishing returns, which we'll go over in a little bit. But basically, what happens is the number of CPU cores you add or the amount of memory, there's a limitation, and also as it gets larger, you get less effect for more money, so it's just a bad situation all around. And there's also the single point of failure, which is even if you have one huge server, that's a single point of failure, which means that something as simple as somebody in the data center tripping over the power cord would take out your server, and then you can serve zero traffic. The solution to those problems, as you might have expected, is horizontal scaling. So instead of having a single huge server to handle our traffic, we have multiple smaller servers that can be scaled up and scaled down. And the additional benefit that's built into this solution is redundancy. So if one of these goes down, the other two are still able to handle traffic. So it increases the reliability of our service, and we don't have any angry users if our one big server goes down. So it's kind of like the opposite. Instead of putting all of our eggs in one basket, we have these backup servers essentially. The problem is that it's slightly more complex up front to build this way, but more efficient long term because you can buy commodity hardware and it's much cheaper when you buy in bulk like that. And recently, thanks to the cloud service providers, we can build on their services, and it basically abstracts away a lot of that complexity. As a result of that complexity related to horizontal scaling, a lot of the kind of buzzword projects you've heard about are generally dealing with those issues. So it's a good time to be a developer because these big tech companies, in a lot of cases, have open sourced some of the projects they used to deal with those issues. So we're kind of building on their work that they invested billions to solve these problems over the course of decades. So Hadoop, for example, if you're working with huge amounts of data, like at Google where they're working with petabytes, it's impossible to get a machine or a server that can handle petabytes of data by itself. So what you do with Hadoop, which is based on MapReduce, it breaks up a massive amount of data and splits it off so that it can be worked on by thousands of different servers, and then it puts that data back together. So those results come back in, and it's essentially abstracting away all that complexity related to handling those thousands of servers. Docker is also a similar case where it allows you to put your applications in containers and easily deploy them to various servers. And built on top of those containers, you can think of Kubernetes or K8s, however you pronounce that. It abstracts away a lot of the complexity, again, of dealing with all those different servers, and that was spun out of Google as well. So that's why a lot of people, even if you don't necessarily know what all these things do, that's why people are so hyped about this stuff, is because it allows you as a small company to not have to invest billions of dollars trying to solve this stuff, and it can kind of just magically allow you to scale your applications. Now let's take a closer look at some of those trade-offs that we mentioned earlier, but I didn't really go into too much detail on. So first is the diminishing returns of vertical scaling. So if we look at this chart, we can see the blue is 1 CPU core on the server, and it gradually goes up to 8. And you can see, so 1 CPU core, 2, you get almost a double increase in improvement. But then once you go to 4 CPU cores, you can see it gradually drops off here. And once you go up to 8, you barely get any performance bonus. Even though you're paying double the amount of money or more in some cases for those extra cores, you're not getting twice as much performance. So this is basically the limitation to vertical scaling, is that you keep pumping in more money, but you're not getting as much return on that investment. And plus, like I said, you're still at risk of not having that redundant server, and that brings in all sorts of issues. So the next trade-off is latency. So a benefit of horizontal scaling is that you can have your application running in multiple data centers all across the world. This is a map showing where all of Google's data centers are located at. And this is very important if you're doing something like online video games where people are playing against each other. You need these people to be able to, as quickly as possible, make contact with your application so there's no lag. If you had one single big server located in the USA, somebody in Australia is going to have big issues. And that's because when your requests and your data is going through a fiber optic cable, it can only travel at the speed of light, which is fast. But in something like an online shooter, even a couple milliseconds delay is going to cause issues. So a built-in bonus of horizontal scaling is that you can have your application running in multiple data centers around the world and reduce that latency and boost the user experience for people using your application. And finally, to kind of summarize everything in a single chart, we can see our extra capacity and our price. So initially, this horizontal, you can see the price is higher because of that extra complexity, but as we begin to scale, it becomes more linear because we've paid the upfront cost of designing our system to work and be able to scale horizontally. With the vertical scalability is you need more capacity, those components, those servers get much more expensive, and eventually it just becomes impossible. You can see it's going exponential. So past a certain point, if you're trying to vertically scale, you're going to have to transition over to a horizontal scaling system and change up the entire architecture of your app, which obviously rewriting takes a lot of time and money from an engineering perspective. So we've gone over some of the high level stuff and also some other helpful info related to system design. Now let's look in depth at the specific components that make up a system, starting off with load balancers. So what are load balancers and what do they do? It's kind of in the name. They balance incoming traffic to your application and can then distribute that traffic across multiple servers so that none of them are being overloaded or underutilized. The reason we want to do this is that it improves reliability and scalability of our web application. It can allow us to add or subtract servers for dynamic scaling. So if you have, let's say like Amazon, during Christmas season or Black Friday, they have way more traffic than usual. A load balancer would allow them to scale up on their back end during those peak traffic periods, and during less busy times they could scale down and save money. It also increases reliability, so instead of having one single point of failure, we can have multiple replicas of our app running on the back end, and if one of those has a hardware failure or something like that, we can route that traffic to another replica and our service will stay up. There are two types. We have software or hardware-based load balancers. An example of software are Nginx and HAProxy, which are gaining in popularity because they can run on any commodity server. F5 and Citrix are hardware-based. They can handle tons of traffic because they're specifically designed only to be load balancers. But one of the reasons these are falling out of favor is because it can lead to vendor lock-in, and each of these things costs like $10,000 or more. It can go up into the hundreds of thousands for very big data centers. Now let's get a visual so you can kind of picture this all in your head and understand it conceptually. So what we have here is your standard setup where you have users, they make a request, the internet then routes that to your domain, which is an IP address behind that where your web server is. Your web server will be something like Nginx or Apache, which you may have heard of, and that web server will then route it to your application. That would be something like Express.js, LampStack, Django, WordPress. Your application is the code you write, and that will interact sometimes with the database or just deliver back some content, like a blog post or something. This works perfectly fine for most cases, just because you don't need to really over complicate it. But for stuff that's mission critical or that's taking a lot of traffic, you don't want this single point of failure. In this case, if this web server goes down or the server that it's hosted on goes down, nobody's going to be able to access your website. So for more basically complex apps that people or businesses are relying on, this is your basic load balancer setup. We now have in between our web servers, we have this load balancer where the traffic is routed. The load balancer can then distribute this traffic to our web servers, and these are essentially isolated. So if one of these even goes down, the load balancer can still direct this to the secondary replica. There's a lot of different ways that you can set up your load balancer to route traffic, and these are some of the most common. So the simplest is probably round robin, where your load balancer has a list of servers that are available, and it will route them by just cycling through each server. So as the requests come in, it'll just continuously cycle through that list and send the next request to that server. The problem with this is that for certain applications, not all requests are the same. Some can have very heavy database queries, and the result could be that just by chance, some of your servers could get hit with a lot of heavy queries and it would lock up because it's doing a lot more work relative to the other ones. Second is least connections. So if you have an app that is doing chat or streaming applications where your users are staying persistently connected to the server, this is a way to make sure that none of the servers get too many connections. The load balancer will communicate back and forth with the servers and keep track of how many connections each is currently serving, and it will route to whatever server has the least at this moment. It will route to that one. Least response time works by similarly communicating with the server, and it times how long it takes for it to respond. So if a server is handling a lot of traffic at the moment, it's going to respond slower, and the load balancer will then decide to respond or to route traffic to the ones that are currently not as slow. IP hash is useful for when you need to kind of maintain a session. So what happens there is that for certain applications, the client needs data that's stored on a particular server. So the way you do that is that you hash their IP address, and that way every time that user sends a request, it will always go to the same server. An example of a use case like that would be for like a shopping cart. So if Amazon, they have tens of thousands, maybe hundreds of thousands of different servers, they're going to have your shopping cart stashed on one particular server. So they want to make sure that when you refresh a page, your request is sent to the same server that holds that data. There's two main types of load balancer, which is layer 4 and layer 7. Layer 4 is simpler, it has access to less data, and as a result it's faster because it doesn't have to use as much processing power to look at each request. This can lead to uneven traffic because it doesn't have full access to the request itself, but a benefit of that is that it's good on the edge of your data center or of your network, because it can look at the IP address, and for example, if you're getting like a denial of service attack or some bad actors going after your application, instead of wasting processing power allowing it through to your web server or your application server, you can just toss that request right at the edge. So a lot of data centers will first route all incoming traffic through a layer 4 load balancer before allowing it further into your application, basically. Layer 7 has full access to HTTP protocol and the data of the request. It can also terminate SSL and decrypt traffic and stuff like that. It can check for authentication, so if a user sends a request, they're not logged in, they're trying to get to a certain page, instead of letting that go to your application server right at the load balancer, you could redirect those people. And as a result of having access to the entire URL of the request and all the data within that, you have a lot of smarter routing options. It is more CPU intensive to run a layer 7 load balancer, but with the drop in cost of hardware in general over the years, it's really not a big factor anymore. Finally, let's look at an actual production load balancer setup. Earlier we just had a single load balancer, which would be kind of stupid because we talked about single point of failure. If you have only a single load balancer, you've just moved the problem up a little bit. Instead of having a single web server, you now have a single load balancer. So in production, what the general setup is that you have your active load balancer, which takes the traffic, but you also have a passive load balancer as well. So these will be in communication with each other, and if the passive load balancer detects something wrong with this, the traffic will then be routed to the passive load balancer, which starts taking that traffic while this is repaired or fixed with whatever's wrong with either the hardware or at the software level. And behind this, it's then just the same thing where you have all your different web servers and applications that are accepting that traffic. So that's it for a brief overview of load balancers and the general concepts. There's a lot more details for advanced use cases, and you can look those up, but this covers kind of the broad concepts of what they are, why you use them, and the general setup. Next we have caching, one of the most important tools for scaling applications. So what is caching and what are the benefits of using it? In simple terms, when you cache something, you take data that would normally be stored on a hard drive or on disk and you put it into memory. The benefits of this are you improve the speed and performance of your application, and as a side result of that, it saves you money long term. If we look at how it works, you can see we have our client that makes requests to our server, and what's new here is in between the database and our app server, we have our cache. So if you look at, in this example, you have a request. If that data is already in the cache, it can serve it directly back to our application, which then sends it back to the client. Down here is if we don't have the data already in the cache, we have to make a round trip to our database, we return it, and then we take it back to our app server. So the benefit of this is that delivering that data from cache is much more efficient and much faster. So reading from memory with cache, you're going to see, depending on a couple different factors, 50 to 200 times faster read performance compared to just reading it from your database. As a result of that, we can serve the same amount of traffic with much fewer resources, just based on simple math of if you're doing something 200 times faster, the same, let's say, server with however many gigabytes of memory, it can serve much more, or many more requests per second with the same amount of resources. Another benefit is that you can pre-calculate and cache data in advance. So this is something that Twitter does with their timelines. They know that users are going to want their timeline very fast, so they'll occasionally pre-compute what your timeline is. So maybe 200 tweets, they'll push that data to cache, and then they can serve it very quickly. So instead of every time you request Twitter having to go to the database, run their algorithm to get your newsfeed, they pre-calculate it and they can serve it within milliseconds rather than a couple seconds waiting for all that to process. So if you know what your users are going to need in advance, you can really improve performance that way. Another big benefit is that most apps have far more reads than writes, which is perfect for caching. So again, if you think of something like Twitter, where a single written tweet, so you write a tweet to a database, it's possible that that single tweet will be read thousands, or for a bigger account, millions of times. So instead of having for every one of those reads going to the database millions of times, you can put that into cache, and it just gets served directly from there instead, which will really help the performance of your application. Let's take a look at a real-world example of how this kind of works and how it can make more sense to you maybe, which would be we're going to use a club with a bouncer and people who want to get in. So this is, our club is essentially our application. Inside here we have the owner, who would be kind of the database. Our bouncer has the password to get inside, and we have our people who want to get in here. They're like clients or users in a web application. So one way to do it, the smart way, that would be like caching, is the bouncer has the password in memory, literally in this case, in his memory. And all these people that ask, they say, hey, this is the password. He says that's right, lets them in. That would be very fast. The other way is, theoretically, he could, every time somebody gives him the password, he walks into the club, goes all the way to the back room, asks the boss, or in this case the database, hey, is this the right password? Comes back, tells them yes or no. So that would obviously take many times longer for every single one of these people, and in real life, these people would get really pissed off because, like, what is this idiot doing? Why is he continuously going back to the database or going back to the owner to get the exact same information? And that's kind of how you can think about it with a web application, is why would you continuously do the same work? A lot of your data in your app is going to be the same data getting constantly requested. Like we talked about earlier with tweets, they're asking for the same tweet again and again. Why would you continuously hit your database for that same information? You're much better off storing it up front in your cache, and that's just a better way to build your systems. You can also use caching at multiple different layers, not just in front of your database, the main ones being DNS, content distribution network, CDNs, your application, and like we've looked at, the database itself. Here's a diagram showing this. So you have your client. When you type in like google.com, for example, you don't actually go to Google, you go to an IP address, and to get that you usually have to access it from a DNS server. So instead of going back and forth every time to find the proper IP address, it usually makes that request once and then it stores it on the client so you can go to it directly. So that's one layer of caching. You then have content distribution networks. So that's, if you've heard about Cloudflare, you're probably familiar with it because every few months it'll go down and like half the internet will go down. So a lot of websites use these, and this is another way you can store up front instead of having to get static files, usually like pictures and videos. Instead of serving them from your own infrastructure, you can push them to these CDNs, and that will boost performance. They'll serve them back directly. You then have your app layer, and like we said earlier, your cache here. And most databases also have internally, we have inside frequently accessed data, they'll automatically cache that as well. So you have multiple layers all across your application where it takes advantages of the speed boosts from utilizing caching. Here's some pseudocode with Python, kind of simulating how you use a cache in your application. In this case, we're just using a built-in dictionary or hash table to simulate this, because that's what a cache really is. Like Redis or Memcached, it's essentially just a giant in-memory hash table. So you see we got our cache, we look up a key value, in this case it's a tweet, so we look up that tweet ID. If that returns data from the cache, we'd return that directly. Otherwise, we do a database query with that ID, we return the data, we set that into the cache, and then we also return it. So this time, when we do this, the next time a user requests that same tweet, it'll hit here and it will return, so we don't have to make that database query. For writes, we've got a similar setup where it's just caching. So in this case, if we're updating a value, we go to our database, we update the tweet, and if the tweet is already in the cache, we want to make sure we remove it so that we don't have an issue with what is called stale data, and we'll go over that a little bit later. But what that is that we don't want users seeing the old version of the tweet or whatever data we just updated, so we remove it from the cache so that the next request, if we go back, it will re-grab that from the database, and that way we're not getting old data for our users. Building off of simple caching, we have what's known as distributed cache, which it works the same way, but it has built-in functionality to replicate the data, shard it across multiple servers if our amount of data is too big for a single server, and then locate the proper server defined for each key that we're using. The main reason you do this is that at scale you don't want your entire system to break down just because your single cache server goes down. So you want some replication and stuff like that so that your system is more reliable. You can visualize it here, so you'd have a active server, you have multiple with different keys, so you have ABC, and you also want sitting here your passive. So if one of these goes down, your application will be able to detect that, and it will reroute to your passive server, which is now the active one. It might seem wasteful, because what you want is basically these are going to be identical. They're going to be in communication and have the same amount of data, but these, under ideal conditions, will never actually do anything. Best case scenario is you never have to use your backups, but the reason you have this is that if this cache goes down and all of a sudden all those queries are going to your database, you're going to have big issues, because your system is built assuming that, let's say, 90% of your requests are going to be served from cache. So if these goes down, all of a sudden your database are going to be overwhelmed by that amount of traffic. So you have these backups, and that's what that's going to help with. Another big thing is that something Facebook wrote about early in their company history was that they had big issues with, they didn't have this they called it a warm-up, where they didn't have this data put into these caches. So they'd spin up, this would go down, they'd automatically spin up a new one, but the issue was that they'd have 100% cache miss initially. So everything would go straight through it because it's empty, and then it would have to fill up gradually. So one of their solutions to this problem was they would do what they call a warm-up, and before they even brought these online and made them available, they would query the database and fill up these caches so that they didn't have that issue. Moving on, a key concept is cache eviction. We need this for two reasons, which is, like we talked about earlier, we want to prevent stale data. We don't want something sitting in cache for too long, because if it's updated, we don't want out-of-date stuff being served to users. We also want to only cache the most valuable data to save money and resources. There's a lot of stuff in your database that might never or very rarely be requested, so it doesn't really make sense to store that stuff in cache, because it's just kind of a waste. So the first major thing is TTL, time to live. This is where you could set a time period before cache entry is deleted automatically. This is mainly used to prevent stale data, and the time that you set can depend on how essential it is for data to be fresh. So in some cases, let's say a blog post, it's very rarely going to be updated, so you could probably set a longer cache time. Same thing for something like tweet counts. Like if you have a tweet and you have a certain amount of likes, it doesn't need to be immediately updated. If there's a few seconds or even a minute where you let that serve stale data, it's not a huge deal. It's not like there's people's lives depending on the exact accurate count on the number of likes on a tweet. In other cases, for something that's very important, like something related to healthcare where it's somebody's heartbeat count or their breathing rate, that you probably don't even want to cache. You want it to be constant live data so that you don't have a delay, because that could literally kill somebody. So you don't want that. The TTL time, it kind of just depends on what kind of data you're working with. So LRU and LFU are two other strategies. These have less to do with preventing stale data and more to do with trying to keep our most requested data in our cache. So least recently used is once our cache is full, we can't obviously add any more keys, so we have to choose what do we get rid of. So this strategy, what happens is whatever hasn't been accessed or what was last accessed latest, we get rid of that because it's not being as frequently requested, so it's less risky for us to drop that. The other one is kind of similar, same concept, which is it tracks the number of times a key has been accessed, and once our table is full, it will get rid of whichever one during that time period has been the least requested. So the concept here is that we want to make sure that highly accessed data, we keep that in cache. Less requested stuff, it's a little bit safer to request that from the database. Some examples of this in practice, we'll keep working with Twitter. Let's say we have two different tweets, so in our database they're the same size, but there's a big difference between a tweet from 2012 from a small account with 10 followers versus a tweet that was just created by an account with millions of followers. The one from 2012 or whatever year it was barely is ever going to get requested, so it's not a big deal if once a month somebody requests that from the database. On the other hand, the recent tweet is going to be there's going to be read requests millions of times for it, so we want that in our cache so that our database isn't getting destroyed by all those requests. Another example related to cache eviction is from a Facebook case study. They called it the thundering herd problem. So they'd have a situation where some user would update a post, like a popular user updates a post, they dump that from cache. When you have thousands of requests coming at the same time, when we looked at our pseudocode, we talked about on the second read request after we updated, they'd just refresh it. But the problem is when you have thousands or tens of thousands of requests every second, what would happen is that a bunch of them at the same time would go straight through the cache and still make that read request, which would cause tons of issues from their database. So their solution to this issue at scale with cache eviction was that they would implement what's called a lease. So they'd have kind of like a backup cache that would still serve that old data while the cache updated in the background. So that's something you probably won't have to worry about, but it shows that at scale, stuff that you really don't even think about, like what would happen if I get thousands of requests during the split second where something updates and gets removed. Most applications don't have to worry about that, but it's kind of interesting that at large scale, all sorts of things pop up that you'd never really think about. So there's a couple different caching strategies. The first one I showed with the pseudocode is cache aside, and that's definitely the most common. Write through and write back are kind of interesting because there'd be more for a write heavy application. So write through, what happens is that to increase the amount of writes the database can handle, the cache is actually updated before the database. What this does is it allows to maintain high consistency between your cache and your database, but as a result, it adds latency to whenever a user writes, so it's going to slow things down from that perspective. The write back strategy involves writing cache directly to, or writing data directly to the cache, which is very fast, but A side effect of that is that if your cache fails before it can write that data to your database, you have an issue with data loss. So that's kind of a riskier strategy, but if you really need to scale writes for some reason and consistency isn't essential, that's one way to do it. And finally, we have cache consistency, which I touched on earlier, and that's basically amounts to you want to make sure that your cache and your database are showing the same thing. The importance of that, if there's a slight delay, it depends on your use case. The biggest thing is that for writes, you want to make sure that the user who's writing data gets that fresh data immediately. Facebook wrote about that, where they had issues where users would update a post, maybe they made a typo, they accidentally posted something they didn't mean to, and they had a delay between when they would write it and when the user would see it, and the users were obviously getting upset because they wanted to immediately see that it was showing the new updated post rather than the old one, because in some cases if you post the wrong image or something, there could be big issues. So that's an example where cache consistency is important. You don't want an old piece of data showing to other users for a long time. Now let's talk about databases. Database scaling is one of the most important topics with system design, and that's because for any large-scale application, the database is usually going to be where your performance bottleneck is, and that's because while your application servers are essentially stateless, so you can scale them horizontally as much as you need, all those servers are going to be hitting the database for retrieving data or writing new data. So what I'm going to be going over is some basic and the simplest ways to improve database performance, and then some more complicated stuff like replication and partitioning. A key piece of information to keep in mind when you're planning out how to scale your database is that most web apps and applications in general are very read heavy. It's usually around 95%. And if you think about that, something like Twitter, one large account, they write once to the database to create a tweet, but that one tweet can be read and retrieved from the database millions of times. Same thing for Facebook with posts on there, and Google when they index a piece of information, that the metadata of that web page isn't going to change very frequently, but a lot of people are going to be making searches for those web pages. So in almost all cases, you're going to want to prioritize and build around the idea that your databases are going to be receiving a lot more reads than writes. So these are the simplest ways to start off when trying to improve the performance of your database, and I'll just go over them one by one. So the easiest is obviously vertical scaling. You don't have to change anything, you literally just move your database to a bigger server so that it has a faster processor or more memory. You then have indexes. So what happens with this is that you create an index based on a certain column that's frequently accessed. So it could be something like the user ID or something like that. It speeds up read performance by creating an index that speeds up the lookup, so it doesn't have to do full table scans across your database. The downside is that writes and updates become slightly slower, and that's because every time you update a row, you also have to potentially modify the index. And you also require more storage for a table that's indexed because you have to store the index itself. Denormalization is where you actually go against a standard best practice with relational databases and you add redundant data to tables so that it reduces the amount of joins you need to do, which improves your read performance. Downside is, once again, we're sacrificing write performance and we're risking inconsistent data across tables, because if you have something that's, let's say, it's in two tables now, you have to somehow figure out a way so that those values, when you write to one table, it also changes that data in the second table where the data is also located. Otherwise, you could get a situation where somebody tries to retrieve the data and the value is actually different in two different places. So you then have inconsistency, which for certain applications could be a major issue. The other factor is that the code becomes harder to write because you have to deal with that situation where you're not only writing to one table, but you have to update that data in every place that that column is now located. Usually that's abstracted away by some sort of library, but somebody has to create that library to handle that. Connection pooling is a pretty simple thing to do. Kind of a metaphor or a way to think about it is it's like carpooling, where everybody just rides in the same car to save resources or save money. In this case, what's happening is that instead of every application thread using its own connection, they're pooled together and kind of use the same one. So it saves on overhead of independent connections to your database. One of the most important ways to scaling your database server is actually not directly related to the database at all. It's called caching. And what the cache does is it sits in front of your database and it can serve traffic from memory rather than having to read from disk. And what this does is drastically improve performance. So for example, you have a client requesting data. For the first request, it would have to pass through the cache because it's not located there and get it from the database. But then the database or the cache would store that result, and for any subsequent requests, the cache would serve that directly. And it's basically the best way of scaling your database is to not let traffic reach your database at all. And cache, because if you're familiar with the difference between like random access memory, RAM, it's much faster than reading it off of whatever storage you're using. Facebook, for example, it's pretty much the most important part of their infrastructure. They released a paper about caching in 2013 that said about 99% of their requests are served from cache. And it's pretty much the most important part of their system because anytime their cache servers went down, the databases couldn't handle all that traffic hitting them. So their entire goal with engineering is basically to protect their databases from all that traffic using their cache. The only real issue with caching is that you can't use everything with the cache. So dynamic data that's frequently updated, it's not going to work very well. And that would be something like real-time driver's location. It's getting updated every couple seconds. So you're going to have to keep hitting that database to get that data. So that's pretty much it for what you'd call easy wins. And now if you have to continue to scale your database, you're going to have to start doing more complicated stuff and start making trade-offs. And that involves replication and partitioning. So your first option is going to be read replicas. And the way this works is that you essentially duplicate your databases and you have what's called a master. This will handle all new incoming write data. And then you have replicas that handle anything requesting data. These handle it to take traffic load off this master. The issues that come in with this are that you run into consistency issues. So let's say something goes wrong in your data center, this connection between the master and the replica is broken, and now you have client requests coming in, and this, because it's not being updated, will have stale data. So depending on your application, that could cause big issues. It could frustrate users because they're seeing the same stuff. They're not getting access to the newest data or the most recent data. And that involves, to take care of that problem, you have to put a lot of engineering effort to handling, detecting when a database is down, bringing it back up, rerouting traffic to your other databases. A side benefit of this, though, is that you have built-in fault tolerance because, like I said, if one of these goes down, you no longer have just a single database handling everything. So even if one of these goes down, you still have these backups. So an additional benefit to handling more traffic is that you also have fault tolerance in the case of some sort of error. Now we move on to partitioning, and the first type, which you probably heard about, is called sharding. So this is horizontal partitioning, where the schema of your table stays the same, but it's now split across multiple databases. The big reason for this would be if your read replica setup, you need to handle more writes. So you split this up. So in this case, we'd be doing it by like name of the user. So you have letters A through M. People's names A through M are stored on this shard, and this one N through Z is stored here. The big upside, of course, is that you can now handle more traffic. The downside is what's called hotkeys. So let's say like XYZ, those names aren't going to have as much traffic as certain other letters. So it can result in uneven traffic if you're not careful about how you're sharding your database. You also have issues that you can't join across these shards because the data is separate. If you do, it's going to be very slow. A famous example, like a hotkey issue, was Instagram. They talked about it with Justin Bieber. So his name or his user ID had way more traffic than the average user, and there's really no good way to handle. Whenever he'd post a picture, their servers would go crazy. So that's, in some cases, there's really no good way to actually handle sharding. You just have to kind of deal with it. So sharding was horizontal partitioning. You also have the option of a vertical partition. So in this case, you're actually dividing up the schema of your database into separate tables. Typically that would be done by functionality. If you have one big row of user data and you realize looking at your analytics that in some cases certain amounts they're not really used together, it would make sense to split those apart so that you're not retrieving a bunch of extra data you don't need, and also it would reduce the size of each database because you're essentially, in this case, splitting it in half. Examples of this is, once again, Instagram. In their case, they actually completely split off the like counts for photos from everything else, so it has its own custom data store so that they can have the performance they want for like counts on a user's photos. Generally, this is easier to implement than sharding, but the downside is that you could potentially end up having to shard or horizontally partition anyway, and then it can get really complicated because you've already vertically partitioned, and now you, even though you try to avoid it, you still have to shard anyway. So by this point, we've pretty much destroyed everything that's considered a benefit of a relational database. Normalized data is gone, strong consistency is gone, a simple data model is also gone. So we've made so many trade-offs trying to scale this that it's almost unrecognizable compared to a standard SQL setup. In this case, it's when you might consider some sort of NoSQL database. The thing to keep in mind is the reason you choose this isn't because NoSQL or NoSQL is magical. It's the fact that up front you know what you're sacrificing. When you started off with a relational database, you kind of thought you'd stay with all the best practices, and by the time you've ended up scaling, you've already lost all that. So the reason you choose a NoSQL database is that you know exactly what you're going to be sacrificing. You know what specifically you need for your application that you can make a trade-off. So if you're doing something with like transactions and banking, you obviously want consistency, but for stuff like Google or social media where you don't need perfect consistency right away, you could make those trade-offs for scale. So it's kind of the devil you know. With NoSQL, you upfront are making the choice, and that way you don't have any surprises down the road. Now let's put all the stuff we've gone over into practice with an example like you'd see in a job interview. We'll go over how to design a YouTube clone, starting by defining the requirements, estimating capacity requirements, going over the high-level design, and finally looking at each individual component. So the requirements are going to be uploading videos, being able to view those videos, a basic search functionality so users can find videos based on a certain keyword, track the stats like view count, likes and dislikes, and basic commenting on those videos. During an interview, you're going to have a very limited amount of time, so it's always important to make sure that you ask the interviewer what exactly they want, and if you're confused at all, it's always better to clarify before you make any false assumptions. For example, like here, you can note that there's a lot of features missing from the actual full-fledged YouTube app. There's no recommendation algorithm, no creator dashboard. A lot of those smaller but important features are missing, so you don't want to waste time thinking about and building features that the interviewer hasn't even asked for. Now that we have our requirements for the project defined, we're going to want to make some basic capacity estimates so that we can, like if you're proposing a project at your company, you want to be able to give a rough estimate to your boss or whoever of how much resources you're going to need. So in this case, for a video app like YouTube, the big factors are going to be storage and bandwidth. So the key data, and this is from YouTube's own publicly released statistics, are that they upload 500 hours of video every minute, and 1 billion hours of video is watched per day by their users. So storage estimates, using that amount uploaded per minute, we can calculate the total amount of data that YouTube, or our app in this case, is going to need for storage every day. You can see first thing we do is we're going to convert, so 500 hours per minute, we're going to convert that to minutes per minute. Kind of confusing, but we're going to take that 500 times 60, so that means we're getting 30,000 minutes of video every minute the website is up. We're then going to use 50 megabytes as an estimate, so for every minute of these HD videos, we're going to estimate that as a size of 50 megabytes, because not only are we, and we'll go into later, the components, YouTube and these like Netflix, these other apps, they create multiple copies of the same file, and that is so they can load them faster for different resolutions, different device sizes, stuff like that. So even after we compress it and do a bunch of other stuff to save size, because we have multiple copies, it's going to be around 50 megabytes. That's just our rough estimate. So we're going to multiply the 30,000 times 50 megabytes, and then we're going to divide by 1,000 to convert megabytes to gigabytes. And what that gives us to is 1,500 gigabytes uploaded per minute. And then we take that again, so daily, we take 1,500 per minute times 60 minutes in an hour times 24 hours in a day, and then we divide by 1,000 again to convert from gigabytes to terabytes, and that gives us 2,160 terabytes per day, or 2.16 petabytes of data per day. Next calculation is bandwidth. This is a little bit easier. So we have our 1 billion hours of video watched per day by the users. We're going to make another rough kind of estimate. We don't know the exact amount or the exact data, but we know that users are going to be watching in different resolutions. So some people are going to be watching in 4K, like ultra high HD. Other people are going to be on mobile devices and they might be watching in like 360p. So we're going to take a rough estimate and assume it's kind of a mix match of people watching in HD or standard versus low quality, and we're going to say it's just 3 gigabytes per hour based on that. So you take the 1 billion hours total based on an average amount of data used per hour of video. You divide that by 1,000 to get 3 million terabytes per day, and then we divide that by 1,000, so you're getting 3,000 petabytes and bandwidth used per day for this application. So based on that, you can kind of look at public cloud providers or for storage and bandwidth cost, and you would be able to somewhat estimate the cost to run this application. Obviously, at this scale, you're either going to get huge discounts from any cloud provider, so their publicly listed prices aren't going to be very accurate, or obviously like Google and YouTube, they actually build their own data centers because it's more cost effective that way. But this is just an example. In an interview, you're going to use rough numbers to try to estimate the capacity that you'll need. You don't need to be 100% correct. Now we have our basic database design. So we know that our feature requirements from before, we needed users to be able to comment. We needed some metadata for our database, or for our videos, so that we can search. So we were going to want to be able to search for the title and the description, so we need that to be able to be stored. And we also have users that we're going to want to be able to upload videos or also comment. So our basic, for this, we want relational database would work pretty well. That's what YouTube uses. They use like a highly scalable version, their own custom design to make MySQL more scalable. but at its core, it's a relational database. So you're gonna have your user, which can either make a comment, and it can also link the user to a video. And inside here, you're gonna have a like count because we wanted our analytics for each video, so likes, dislikes, views. And then also for your users, you have a username of some sort, email, bio, and then here you're gonna have just basic comment ID, comment, and the time the comment was posted. Obviously, you can add a ton more information here, and if you wanted a more advanced, like for a channel, you'd probably have a channel table where the user would connect as the owner of a channel, but for our basic database design, this all works pretty well. Now we can start getting into our system architecture, and first let's go with the high-level overview before looking at each individual piece. So we have our clients. This can be somebody from their phone, their desktop, a TV, really anything. They're going to be sending requests. You have your CDN. This is going to be where a lot of your most popular videos are being served from. You have our web server, which is going to act as basically a load balancer and distribute to our multiple app servers we have running in the background. The app server is going to be what's talking. So for like an upload, it's going to send the video to this processing queue because there's a bunch of stuff involved in the background here. It's not really that simple, so we just want to be able to fire off that upload request and then allow the person uploading to do other stuff while this works in the background. This will sit in kind of a queue, and there'll be multiple video upload servers to handle that, and eventually once those are uploaded, it'll get dumped into object storage. So that'll be, you could use some open source thing, or more commonly it's something like Amazon S3 would be the most well-known object storage. So then in addition, you're going to have your user data in a database and your video metadata, which will be used for when we're searching or when our users are searching for videos. So first, let's look at the CDN. For some applications, it's not as important, but for something like a service like this YouTube app, it's probably the most important part because we want to use this to not only take some load off our back end, but also improve the experience for our users. So a CDN is going to have, like if you use something like Cloudflare, you're going to have hundreds of points of presence, as they're called. So instead of having to, like if say we have a user in Australia, instead of having to send that request and go to your data center that's maybe in North America, which is going to, just due to the speed of light and latency, going to be very slow, you can push your popular videos to this point of presence that's in Australia, and it really lowers the latency. And it can also, since it's being served there directly, you obviously don't have to have as much resources on your back end for like the app server. Usually that's going to be, you're not going to store all your videos. Like if in a YouTube situation you have videos that are 10 years old that have 5 views, they're never really, there's not anybody watching them, they're that old. So there's no point storing this on a CDN because there's no demand for it. So pretty typical, you're going to store like your hottest 20% of your videos or some other subset of that. And that way you're saving costs because you don't want to have everything. A lot of your data is not going to be accessed that frequently, so it's not a big deal. Next we have our web server or our load balancer, which is pretty simple. All this is going to be doing is distributing traffic equally among all of our app servers. So if one app server goes down, this will be able to tell and it'll be able to redirect that request to one that's functioning properly. And this also allows us to properly scale our application as it grows. We can keep adding more app servers behind our load balancers, and we don't have to worry about really any bottlenecks here. In more complicated setups, you're obviously going to have multiple data centers, so the web server is going to have to read the IP address or location of the request coming in, and then depending on that, it will route it to the nearest data center. So that's a little bit extra complexity when you're running a larger scale app, but that's also pretty important for user experience. The app server is going to act as kind of the brains of your entire application. It's where like the jargon would be the business logic, and that will determine what is going to be done with specific requests. So if it's a video upload, it will know to send that file and information to this processing queue. If it's a search request, it will query our video metadata database and will return, let's say, like the top 20 results that are most relevant. You could have just basic keyword, or kind of beyond the scope of this, like YouTube, they obviously use like machine learning and a lot more complicated stuff that takes into account those keywords, but they use a lot of different ranking factors. And then you also have, like when you search, you're gonna have to hit both, where along with the video, you're gonna want to pull in some information about the user as well. Like when you click on a YouTube video, it also provides like a link to the user's channel and stuff like that. So you're gonna be querying multiple tables and stuff like that. And addition, there's gonna be comment data as well that you're gonna pull in for each video. And finally, we have the processing queue and the video upload server. So first thing is, the reason we're going to use this queue is to make the whole process of uploading a video less fragile. If you went through like with a standard HTTP request, if the user lost connection at any point during this whole procedure, they'd have to restart from scratch, which would be very frustrating. So what this queue lets us do is, once the file is uploaded, we kind of give it a task ID, and we have the user ID who uploaded it. And then if any part of this fails, we can always just retry whatever specific portion failed. So it kind of gives us more durability in this upload process. So the initial part is going to be getting the file itself. So you're going to have some logic and code to handle partial uploads. There's algorithms so that you just don't get a bunch of the same video, because you don't want to be storing the exact same thing multiple times. So you might want to take into account looking at samples. They take samples of the video and look for identical portions and see if they can save data that way. And then you also have to figure out a way, how do you, if the whole process fails, then what do you do? Do you notify the user? Something like that. So these are all things you're going to want to account for and think about. Once the file has been uploaded and it's in the queue, what you're going to do is you're going to have to encode the video. We mentioned that earlier, where you're not just going to store one version of each video. You're going to want to have pre-created files for every video format, resolution, quality, stuff like that. YouTube, they can dynamically check the user's connection speed, and that's how you'll notice, like, if your connection speed slows down, they'll automatically bump you down from HD to a lower resolution so that the video doesn't start lagging or buffering. So there's stuff like that. That's why you want those multiple files, so you can switch on the fly. You're also going to do stuff like thumbnail generation. You'll take still images from the video and pre-create those so that when somebody searches the video, it's got that image if the user doesn't upload something. And then also, final part of the process is that you're going to move that from the upload server and you're going to put it into object storage so it's more easily accessible. So a quick summary of everything you need to think about while you're doing a system design interview is, first, you're going to want to make sure you define your requirements. You communicate with the interviewer, make sure you know exactly what they're looking for and what they want to focus on during the interview. You don't want to make any false assumptions and end up going in the wrong direction. You're then going to want to make your quick estimates about the capacity, because that's going to influence your entire design. In some cases, they might actually kind of be playing a trick on you. If they give you really small requirements, they're wanting to test to see if you have common sense, really, and make sure you're not over-designing something. If they give you requirements where it's really small, you're not going to need load balancers, you're not going to need duplicate databases and a bunch of crazy stuff like that. So in some cases, you just want to use common sense and make sure you're not overdoing things. Next, you're going to want to design your database, go over high-level stuff. So for database, You're going to want to show how data moves around the app, where it's stored, what you're using to store that data, depending on the specifications. High-level design overview, you're going to want to make sure you point out the main parts of the application, and then once you've done that, you're going to look at the specific components and discuss your ideas for each of those. You're going to want to make sure you go over and show to the interviewer that you understand the trade-offs. So if you're using SQL, relational database versus a NoSQL database, you want to make sure you explain why you made that decision and some of the trade-offs in either direction and why you think that makes sense. Basically, you just want to make sure you're communicating well, that you show that you're not just kind of mindlessly throwing around buzzwords, that you understand what's going on and why you're actually making those choices. So that's basically it. If you have any confusion or questions, make sure to leave a comment below and I'll get to it. Also, if you want to see if you have topics you want covered, be sure to comment about that as well.